Okay, hello everybody. Welcome to lecture number 23, our final lecture in this course. It's good to see you all, and I know it has not been an easy year for anyone who's here, so well done on being here, and well done on your persistence and resilience and positivity in sticking with the year so far and being here. So hopefully it won't be too much longer before we have more opportunity to engage in more direct ways and not so remotely. So our business today really is just to have a little discussion about the exam that's coming up. So as everyone probably knows at this point, the exam has been scheduled for the 2nd of June, which is still nearly 4 weeks away. It's Wednesday, the 2nd of June, so it's 4 weeks from yesterday. It's the late session of that day, 4:30 to 6:30. And so just to be completely clear about it, the plan for the exam is obviously it's going to be held remotely, so everybody will be doing it in their home location. There are 6 questions, which is typical of the format from the last few years in the semester 2 exam in this module. The time for the exam itself is 2 hours, so it's from 4:30 until 6:30 in the afternoon. And in addition to that, there's 30 minutes allowed for upload. So the way we'll manage it is via a Blackboard assignment. So whether you're registered in MA 180 or MA 190 or MA 186, the exam will be posted as an assignment in your Blackboard page, and we'll post well in advance kind of details exactly about the kind of, the logistics for that. And it'll open up on that day at 4:30. And it'll stay open for the 2 hours plus 30 minutes for upload. So that's the plan. The experience so far in the winter exam session has been that that's ample time, typically, for upload. So if anybody runs into any problems regarding connectivity or anything like that, and hopefully it won't happen, but of course, it does happen to everybody occasionally, but not too often. If anything like that happens, just get in touch with us. We'll sort it out. So, but hopefully everything will work on the day, and we'll be able to do that. So the plan is to basically write the answers as would be typical in any other year by hand on A4 paper, and just scan them and convert your scan to a PDF format. And an app that many people find useful for that is Office Lens, and then just upload it to the Blackboard as a PDF file. Okay, if there's some sort of major sort of connectivity issues or failures of technology or anything like that, get in touch with us on the day and we'll figure it out. But typically this works reasonably reliably. If you haven't used Office Lens before, it's a handy app that just converts basically photographs or anything like that to PDF format. And if you just Google Office Lens NUI Galway, there's an advice page for students on that about how to use Office Lens to convert documents to PDF format that are created, for example, by handwriting, and upload them on Blackboard. So it's quite straightforward, I think. So if anyone, but I'll post a link to that page on the website in case anyone hasn't done this before. And indeed, we can do a practice run of just practicing uploading something to a pretend Blackboard assignment via the MA 180, MA 190, MA 186 pages in advance if anybody would like to. Okay, so the arrangements are the same for the exam across the 3 codes for this module. And in terms of the questions, so we've talked about this before, but just to recall it, there are 6 questions in total, and you have to answer all of them for full marks on the exam. So the 3 calculus questions are the first 3, as it happens, and the 3 algebra questions are the last 3. So the 3 calculus questions, I can only really comment on those in terms of content. They'll match the 3 chapters of our lecture notes and the 6 homework sheets. So the first 2 homework sheets match the first chapter on integration. The second 2 homework sheets match the second chapter on the real numbers and subsets of the real numbers, infinite sets, countable sets, supremums and infimums, and so on. So that content from chapter 2 would be the second of the 3 calculus questions. And the content from chapter 3 on sequences, convergence, series, Maclaurin, series representation of functions, that will be in question 3, and it matches the last 2 homework sheets. And as you know, the final homework sheet is open currently and due tomorrow. So this year, and also, I'm not sure about last year because I didn't teach this course last year, but 2 years ago, the 2019 summer exam, we had the exact same format. The calculus questions each had 4 parts, A, B, C, and D, all carrying the same marks. So it's been the format for several years that we've had the 6 questions, 3 calculus, 3 algebra. This year, and 2 years ago at least, the calculus questions each have 4 parts, and the 4 parts all carry the same marks. That's just sort of for consistency and sort of convenience, I guess, that they're divided up that way. So general advice, we'll have a look at a couple of sample questions in a minute. But I suppose the general advice is, it's not a long time, 2 hours to answer 6 questions. I think the questions are not long, but still you have to be, you have to keep it moving to get through them all in 2 hours. So first advice is, read the questions carefully and make sure that you answer exactly what's asked. It does happen to people occasionally that they sort of accidentally answer something that isn't exactly what was asked, and that is an unfortunate thing to happen. but it can happen if you're just not really careful about how you read the questions. And the other thing, I suppose, about assessment generally and about exams is, when I'm reading what you've written in an exam, my job, and also when I'm setting the exam paper and other assessments, my job is to consider whether I can establish whether you've achieved the learning outcomes of the course or not. And your job is to show me that you have. Okay, so basically, I suppose a general piece of advice is when you're preparing for the exam, think about the learning outcomes for the calculus module and the learning outcomes at the end of each section, and just sort of, keep an eye on those, because I suppose that's what I'm supposed to be assessing. Have you achieved the learning outcomes, and can I certify that you have? And so again, equally on that, this is a very imperfect process now more than ever, that we have to communicate with each other in this way, that I make up some questions, convey them to you, you answer them on paper, and then sort of, send me your answers and I read them. So it's not a very direct form of communication. But what you have to do, I suppose, is communicate to me when I'm reading your script that you have achieved the learning outcomes, so that I can happily confirm that you have. Okay, so just bear that in mind, that it's not just a question of kind of figuring out what the answer to the question is and writing that down. It's a question of showing me also that you have actually achieved the learning outcomes. And I don't mean that you have to write extensively. I just mean kind of keep that in your mind. That this is an exercise in communication, even though it might not be a very ideal one. That that's what you're trying to show me, that you've achieved the learning outcomes. So that's general advice. I suppose in terms of looking at old papers or knowing what to expect or anything like that, there are plenty of old papers out there. I wouldn't advise you to kind of rely overly heavily on old papers, because this is not like the sort of state exams in schools where the exams are set by some kind of external agent and your teachers don't know what's coming up. This is different. We are responsible for the assessment and for the communication throughout the semester. So, and this year's exam is, of course, based on this year's version of the course. On the other hand, there are exam papers from previous years available. And, the general style and format, I would say, is typical of recent years in this particular module, at least as far as the calculus is concerned. So if you have a look back through the last couple of years of summer exam papers in this course, you'll find examples of the kind of things that are typically asked. The structure has been the same for a few years in terms of the 3 chapters and the 3 kind of general topics that are covered by the 3 calculus questions. So definitely, I'd say, if you're looking for sample questions, practice questions to kind of give you a sense of the style and flavor of questions that are likely to appear, have a look back at definitely the last few years of papers. And just when you do that, you'll see that on the front page of the paper is written the names of the examiners from a given year. So, if you see some papers that are written by me, you can sort of, I suppose, you get a sense of the sorts of questions that I have asked in the past. So I didn't teach this course last year, but I did the previous year. And I didn't in 2018, but I did for a few years before that. So you'll see those papers. And the other ones are also sort of fairly similar, So that's some general comments and general advice. Does anybody have a question or a comment right now? So what I propose to do for the rest of this time this morning that we have is just to have a look at some sample exam type questions, which I think are kind of reasonably representative. Like don't read too much into these samples, because they're only meant as an indication, so don't sort of overanalyze them, but they are meant as an indication. Okay, if nobody has a question or a comment, I will fire ahead and have a look at a sample question. So maybe what I'll do, because of the fact that we looked at a sample exam type question from chapter 2, when we finished our work on chapter 2 there a couple of weeks ago, in week 9, I think it was. There's a lecture in week 9 devoted to a sample exam type questions from chapter 2. So maybe today I'll just focus on the chapter 1 and the chapter 3 question. And if there's time at the end, I'll come back to the chapter 2 one, but we can glance at least at all 3. So if I say anything here that doesn't make sense, please just shout and don't be shy about that. Okay, so 3 questions for calculus. Each of them will have 4 parts labeled A, B, C, D. So these sample questions are supposed to sort of reflect that and to indicate the format. So the first question is on our chapter 1 of our lecture notes, which was about integration. And, typically we have, of course, for that chapter, lots of different techniques of integration. So what I will ask you to do is, 4 integration problems. One of them will be about the fundamental theorem of calculus, and the rest of them would be basically examples of integrals to evaluate or to calculate. So this is kind of typical. And, we have various techniques of integration. We have integration by parts. We have substitution techniques. We have a partial fraction method. And we have sort of, I suppose, kind of general direct methods as well. So these are the kind of things that will turn up here. And so you'll have 4 parts to answer. Okay, and typically the first part is the one that's about the fundamental theorem of calculus, but I'm certain that's always the case. So, okay, so Maybe just a quick thing, and I suppose I'll try to say something about, under exam conditions when you have time pressure and everything, what would be considered to be a sort of sufficient answer to a question like this. So our first question here, maybe I'll answer this one just up in the top corner of this slide and make a total mess of it, and then the other ones I'll answer on the next page. So supposing you were dealing with this one. So part 1 here, draw a diagram that indicates the meaning of this function a. So let's have a look at this function a of x. So a of x here is the integral from 1 to x of the function square root of t over t. And so it's one of these area accumulation functions that we had back in chapter 1. So we are asked to draw a diagram that indicates the meaning of a of x. So I guess what I would like to see here would just be some picture that shows me that you know what it is that this function a is measuring, that it's measuring area under a graph. So our picture here maybe would be some kind of picture of the Cartesian plane. The left-hand endpoint in the picture here is 1. So we're integrating from 1 to x, and our function that we're integrating is y equal to the square root of t. So like, I'm not too pushed about whether your picture is a kind of perfect depiction of what that graph looks like or not, as long as it's kind of approximate. So the square root of 1 is 1. So y equals square root of t. T is the variable that's labeling the horizontal axis. So passes through the point 1, 1, the point 4, 2, and so on. Looks basically like that. So this is the graph y equals square root of t. And what the function a is counting for a value x is the area enclosed under that graph between 1 and x. So some kind of picture like this that shows that a of x is this area that's shaded in orange would be sufficient. Okay, of course, if you had time in your hands, you could write more about it, and you could write a little paragraph kind of explaining it all, but a diagram indicating the meaning of a of x. So I want to see some picture that shows me that you know what a of x means and what that function does. Okay, it picks up area under the graph of t, and for a given value of x, it counts the area to the right of 1 and to the left of x. Okay, so this is for x greater or equal to 1, of course. It says that in the question. Okay, greater or equal to 1. Okay, so that's part 1. So if anyone wants to shout, please, or put a comment in the chat if I say something that doesn't make sense, please do. Okay, so that's part 1. So part 2, what does the fundamental theorem of calculus say about the function a? So again, there's more than one way to answer this, of course. You can write a sentence to answer it, or you can just write kind of a very brief kind of a few words to answer it. And so as long as your answer shows me that you know what the fundamental theorem of calculus says about this function, I don't really mind what your form of words is. But of course, the fundamental theorem of calculus tells us something about the derivative of a. It tells us that the derivative of a at x is just the value of the function which is being integrated at that x. So it's just the square root of x. Okay, and this would be for x greater than 1. Okay, so that's what the fundamental theorem of calculus tells us about the function a. Okay, and again, like if you want to write something a bit more and write sort of some longer words, that's absolutely perfect. If you prefer to sort of write it in terms of the words, it tells us that the derivative of a is the square root of x. That's fine as well. And there are many ways to say the same thing in terms of the choice of words to use, and I'm not hung up about that at all. Okay, the third part then, what is a dash at 4? Well, a dash at 4 is the y coordinate of the point on the graph y equals square root of t, whose coordinate on the horizontal axis is 4, so it's the square root of 4, which is 2. Okay, so it's just the height of the graph above the horizontal axis at the point 4 in the domain of the function. Okay, so that's all you have to say there, really. And so that what I've written there would be a complete answer to part A. And I would get full marks. There are other versions that you could write as well that would also get full marks. So just if you have a different style of writing, that's completely fine. Okay. So if anyone has a question or a comment, please either put it in the chat or shout. I won't take long pauses. So, but please, if you do have a question or something doesn't make sense to you, do put something in the chat or speak up. Okay, so the rest of this question then. So we've got 3 integrals. So I'm just going to insert a blank page to make this not a complete mess. So part B. Our problem in part B is to calculate the definite integral from 1 to 2 of x e to the 3x dx. And so for this, and remember also, I should have said this at the start, for the exam this year, unlike other years, you will have access, if you want to the lecture notes and to our course resources, basically. You probably won't have a lot of time for searching in the lecture notes if you need to kind of look something up that you're really not familiar with. So I think it's kind of a mixed blessing in a way. But if you want to remind yourself of some formula, or how some integration technique works, you do have those resources available. I'd advise you not to sort of rely too heavily on them, in the sense that there won't be an awful lot of time. But nevertheless, you have the opportunity to sort of check statements and things like that. And definitely, I think, being familiar with the lecture notes so that you know where to find things will definitely be helpful. Okay, this is an integration problem. We have a couple of techniques of integration at our disposal. We have to decide which one will work for this problem and give it a go, see if we can get it to work out. And this is a product of two terms where we have an x and we have this exponential function. And I suppose there's no obvious substitution that will work, because differentiating the exponential function e to the 3x will just give us kind of e to the 3x again. It won't pick up this x part. So this really looks like a candidate for integration by parts. And if you haven't revised this stuff recently, don't worry about it right now. But it's a case where we have a product of two things. The integration by parts formula tells us that in general, if we want to integrate something like uv dash, for instance, that would be the same, whether that would be uv minus integral of u dash v dx. And I suppose, I'm not saying that you have to write this down. Something you might find it useful to do so, to remind yourself. But I suppose if somebody did write that down and didn't write anything else for this question, they'd get some of the partial credit because they've written down something that's relevant. Okay, so in any case, this is a candidate for integration by parts. So if we declare u to be x, basically we can convert the problem of integrating u v dash into the problem of integrating u dash v, which we hope might be easier. If u is x and v dash is e to the 3x, then we can write u dash to be 1, just the derivative of u with respect to x, and we can write v to be some antiderivative for e to the 3x. And of course, if we take an antiderivative for e to the 3x, it would basically be e to the 3x, but we have to adjust by a constant, 1/3. And the reason for that is, well, if we just take e to the 3x, the derivative of that is 3 times e to the 3x, not e to the 3x itself. So we introduce that factor of 1/3 to compensate for the 3 that turns up when you differentiate e to the 3x. Okay, so with that allocation of a and v, of u and v, we can plug everything into the integration by parts formula and basically hope that we can do something with it. So let's do that. So that would tell us that the integral from 1 to 2 of x e to the 3x dx is uv would be x times 1/3 e to the 3x. I'll write it as 1/3 x e to the 3x, evaluated, of course, at 2 and at 1, minus integral of u dash v, which would be u dash is 1, which is good because the u dash doesn't really enter that picture. And so we got minus u dash v, v is 1/3 e to the 3x. So we got minus 1/3 integral from 1 to 2 e to the 3x dx. And now we're in good shape because we can integrate that last part directly. And I guess, if you made it to this point, if you make it to this point, you're probably going to finish the problem without trouble. But, you certainly have at least half of the marks at this stage. Putting x equals 2 in here gives us 2/3 e to the 6. Putting x equals 1 gives us 1/3 e cubed. And then we've got minus 1/3 integral of e to the 3x. So take an antiderivative for e to the 3x, it's e to the 3x over 3 again. So we've got 1/3, another 1/3, so 1/9 e to the 3x, and that also is evaluated at 2 and at 1. So just to finish it off, we've got 2/3 e to the 6 minus 1/3 e to the e cubed. We've got minus 1/9. When we put x equals 2 in there, we get minus 1/9 e to the 6. And then we get minus 1/9 e cubed, so plus 1/9 e cubed. So that's the answer. And if you want to tidy it up a bit more, you can of course say that the 2/3 e to the 6 minus the 1/9 e to the 6 is 5/9 times e to the 6. And minus 1/3 e cubed plus 1/9 e cubed is minus 2/9 e cubed, I guess. If you didn't do that last step, I don't care at all. This is, this answer is perfectly all right for the context at least of an exam. Of course, if you had more time in your hands, you'd present the answer in as neat a way as you could. Okay, so that's part B there. So it's an integration by parts problem, and I guess what you need to be able to do is recognize when your problem is a good candidate for integration by parts and implement the integration by parts technique accurately. And that's sort of what I want to see in terms of the learning outcomes there. Okay, maybe I could squish part C into this last little bit of space. If anyone has a question, fire ahead with your question. So part C here, integrate cosine of the square root of x over the square root of x. Oops. Cosine root x over root x dx. Okay, so here it is not really obviously a candidate for integration by parts, although I suppose you could try. But cosine of the square root of x is a bit of a mess. Like when you differentiate it or try to integrate it, it's not going to give you anything nice. And it's not a candidate for, partial fractions or anything like that. And so I guess it does have a square root of x appearing both in the cosine and in the denominator. And we know that the derivative of square root of x is basically 1 over square root of x. So I think this is a candidate for a substitution, and a good substitution to try is u equals the square root of x, which is x to the 1/2. And I guess the reason why I'm suggesting this is we have a cosine of square root of x. That's not something that we would like to be dealing with. We'd rather be dealing with cosine of u du. Like we know how to integrate cosine of x over x, but not cosine of the square root of x. So if we substitute u to be the square root of x, the derivative of u is basically x to the minus 1/2, which is 1 over square root of x, and the 1 over square root of x along with dx does appear in our problem. So maybe we can rewrite the problem in terms of u and kind of absorb the annoying square root of x there in the denominator into the du part. That's the hope at least. So if we do that, then du dx would be 1/2 x to the minus 1/2, which is 1 over 2 root x, of course. And just rearranging this with the aim of replacing our variable x with u, this would be saying that du is 1 over root x dx. There's still a factor of 2 here, but I'll put it over here. Write that as du. Okay, so this is saying that the 1 over square root of x dx that appears in our problem, after this substitution, we can write that as du. What's left is cosine of u. So really, the problem translates to cosine of u integrated over u, which is certainly a more attractive prospect than what we started with. So let's see if we can do that. So rewriting in terms of u, our problem becomes our integral becomes what have we got? We've got 1 over root x. The 1 over root x dx part is 2 du, and the cosine of root x part is cosine u. And of course, when we integrate cosine u, we get sine of u. This is 2 sine u plus constant of integration. And because the problem was posed to us initially as an integral in x, we should give the answer in terms of x. And this is 2 times sine of the square root of x plus c. Okay, so I guess, it's an exam, so if we have to be concerned about marks. So I suppose one remark is, if you mention the substitution technique, I'll give you probably 1 out of 5 marks for that. If you kind of correctly rewrite the problem in terms of u, you probably get at least 2 or 3 marks out of the 5. If you forget the constant of integration, I have to deduct a mark. So that's kind of how it works. But basically, I will be sort of looking to give you partial credit for whatever is written there that shows me that you know what you're doing and that you know how to go about implementing the substitution technique, even if there's a small mistake somewhere or anything like that. Like it won't cost you dearly if it's just a little slip. Okay, that is part C there, and part D. Part D is a rational function. So we've got integral of x squared plus 3x plus 3 over x plus 1. So again, it's a indefinite integral. And I've got it written down over here somewhere. X squared plus 3x plus 3 over x plus 1. Okay, so here we have a rational function whose numerator has higher degree than its denominator. So the first step there is to just do the log division and see what this thing is. Write this thing as a polynomial, like plus a remainder part that will have a x plus 1 in its denominator. So strategy here really is to divide the x plus 1 into the x squared plus 3x plus 3. If you haven't practiced this long division of polynomials, recently, probably it's a good idea to just remind yourself, although I know that you're doing it in algebra as well with Jane, so probably you have. Okay, so divide x into x squared, you get x. Multiply that by x plus 1, you get x squared plus 2x. Do the subtraction there, you get x plus 3. Divide x plus 1 into x plus 3, you get 1 from the x terms. And you're left with the 2, and that's the remainder. So this is saying that x squared plus 3x plus 3 over x plus 1 is basically x plus 1. That's the quotient when you do the division. There's a remainder of 2, so it's x plus 1 plus 2 over the denominator x plus 1.
Shouldn't it be 1x instead of 2x?
Oh, probably.
In the second line. X squared plus 1x.
Oh, yeah. Thank you. Yep. Yes, I actually got it right in my own notes, and I've got it wrong here. Thank you very much. I'm just going to end up causing more confusion for people than. So, okay, that's the kind of slip that would not be heavily deducted for. If you made the same mistake as me, a mistake like that, I wouldn't penalize you heavily for. But yes, you were right. We should get it right. So it's x squared plus x. So this is 2x plus 3, and this is a 2, not a 1. Thank you very much. Okay. The 2, yeah. So this is 2x plus 2, and the remainder is 1, not 2. Okay. We'll try that again. So this would be x plus 2 plus the remainder of 1 over x plus 1. Is that right? I have it right in the version that I prepared earlier. Okay, so basically that's saying that what we need to integrate is x plus 2 plus 1 over x plus 1 over x. If you get to this stage, you have at least 3 or 4 out of the 5 marks. And integrating x, we get x squared over 2. Integrate 2, we get 2x. Integrate the 1 over x plus 1, and we get log of absolute value of x plus 1. And don't forget the constant of integration, because this is an indefinite integral. We should give a description of all the antiderivatives. Okay. So these are typical. I mean, again, I don't want to give the impression that these examples sort of cover every possible variant that, that I could ask you about. For example, there's no improper integral here, and I might ask you for an improper integral, which was section 1.5 of the lecture notes. But this is, this is typical, and I think sort of, it reasonably well indicates the sort of level of detail that would be expected, hopefully. Anybody have a question or a comment? How much of our final grade for the year will this exam be worth? So it's worth basically 30% of the overall grade for the year, because it's 60% of the semester 2 grade. Okay, thanks very much for pointing out that slip, by the way. I appreciate it a lot, because I wouldn't want to say something that would lead people to be wondering whether the calculation was correct or not. So thanks. If you see another one, please do shout again. Okay, here's sample question number 2. So my suggestion, because we already have a lecture and it's available on the website for week 9, devoted to an exam type question for question 2, my suggestion now is to just sort of glance at this for the moment, and I can add a solution to it later. But basically, the themes here are subsets of the real numbers, bounded, unbounded subsets that are bounded above or bounded below maximum, minimum elements, and the concept of a countable or an uncountable set. So I suppose the remark I'd make is, this kind of thing. Think about whether an assertion is true or false. Give an example to show that it's false, maybe, or a short explanation is something that I might ask you about in question 2. Give an example of a set with some specified properties, as in question part D here. And also, I'll ask you something about the kind of theoretical elements that we had there in chapter 2, the concept of countability, the fact that the open interval 0, 1, for example, in the real numbers is not a countable set. The Cantor diagonal argument. I will ask you some elements about those kind of things. as well as about the idea of a supremum and an infimum, and the distinction between a supremum and maximum, and between infimum and minimum. So I suppose just make sure that you're familiar with those concepts from chapter 2. Chapter 2, I suppose, had the most sort of conceptual content as opposed to kind of practical tasks that we can complete. And, again, I suppose for chapter 2, I hope it'll be useful, the fact that you have the lecture notes at your disposal for the exam. But on the other hand, during the exam is not the time to be sort of grappling with the concepts. The lecture notes are there as a sort of support and reminder, not as a sort of, make sure that you're familiar with the content and the key ideas in advance. Okay, so we move on maybe and have a look at chapter 3, because we haven't looked at an exam question from chapter 3 already. And if we have time, we'll come back to chapter 2, or I'll post a solution later. Okay, so question 3 again. So this is convergence of sequences and so on. So I'd say question 1 is the most kind of practically focused in terms of examples of integration to work with. Chapter 2 is the most sort of theoretical or conceptual, and question 3 is something in between in terms of the balance of practical tasks and more conceptual ones. So, okay, so first part A here. So I want to know that you know what a convergent sequence is, and that you know something about the definition of convergence, and that you know what a bounded sequence is, and that you can recognize a sequence that's divergent or convergent, at least in some instances, and that you know what a monotonic sequence is, one that's either increasing or decreasing. Okay, so maybe the first part A here we can answer really quickly. So a convergent sequence of real numbers. Give an example. So here, of course, there are infinitely many answers to this that are completely correct, and there are also many ways to present a correct answer. So I'm just going to do for now what is kind of, I suppose, the quick thing, and write a convergent sequence of real numbers. Well, yeah, you want a sequence of real numbers that's converging to something. The absolutely easiest way to do this is to just write a sequence of real numbers whose terms are all the same. So, for example, the sequence whose terms are all 1 would be a perfectly good answer to part 1 here. It's a sequence that converges to 1. It's it seems almost like cheating, but it's a perfectly good example of a convergent sequence. If you're not comfortable with that and you feel that it is a bit cheaty, then just I'm fine with it, because it certainly is an example of a convergent sequence. If you prefer something whose terms are actually different from each other, you could write something like 1, 1/2, 1/3, 1/4, 1/5, 1/6, and so on. That's also an example of a convergent sequence. It converges to 0. This first one converges to 1. In fact, all its terms are equal to 1, which is like the strongest way you could possibly converge to 1. So either of those is perfectly fine. I mean, basically, there's any number of examples of convergent sequences that you could write down. In terms of how you present the sequence, again, like in an exam condition situation, I'm not fussed about it. If you write down something that tells me what your sequence is, and your sequence is indeed an example of a convergent sequence, I'll be happy. So, technically, I suppose we could be a bit more formal than just writing down a few terms followed by some dots. We could write down like a formula for the nth term. If you prefer to do that, absolutely fine. If you prefer to write down a few terms with some dots to indicate that it continues, I'm okay with that too, at least in an exam context. Although I think we should also all sort of, I suppose, teach ourselves to use formal notation correctly. But under exam pressure, it's okay to write it this way. The only thing I suppose that I'll ask is, if you do it this way, make sure that you write enough terms of your sequence before the dots to convey to me definitely what your sequence is. So, for example, with the first example here, if you wrote down only 2 1s and then dots, I'd probably say, oh, it's not really clear to me what this sequence is. But if you write down enough of them to make sure that I can see what it is. Similarly with the second example, like if you only wrote down 1 1/2, maybe it doesn't really tell me that the next term is a third. If you write down a few more of them, I can see what your sequence is and what you had in mind. Okay, so basically give me the best chance of seeing what you had in mind, is my advice. Okay, so those are 2 examples of convergent sequences of real numbers. A sequence of real numbers that is bounded and divergent. So again here, I guess the point is, we know that a convergent sequence must be bounded, but it's not true that every bounded sequence is convergent. Plenty of ways, again, to give a sequence of real numbers that's bounded and not convergent. In my opinion, one of the sort of easy ways to do it is to just give a sequence whose terms alternate between 2 different things. So, for example, we could take the sequence whose terms alternate between 0 and 5, 0 and 5, 0 and 5, whatever. Pick your 2 favorite numbers and have a sequence of terms that alternates between them. Okay, again, I think, you could write an equals 0 if n is odd and an equals 5 if n is even. That's absolutely fine as well, and probably in some way technically more complete, but this shows me what your sequence is, and it's fine. Okay. So this is an example of a sequence of real numbers. It's bounded and divergent. Of course, we can easily see that it's bounded because all of its terms are between 0 and 5. There's no term that's greater than 5 or less than 0. It's divergent because its terms continue to oscillate between 0 and 5, no matter how far we travel along it. There's no limit that its terms are converging to. So that's a perfectly good answer to that question. A sequence of real numbers that is convergent and is not monotonic. So again, this is one that, the answer can be written pretty quickly, but I guess you have to put a little bit of thought into thinking about an answer. So we know that sequences that are monotonic and bounded are convergent. Here we're asked for a sequence that's convergent, but not monotonic. And of course, it must be bounded to be convergent. So an example here, I guess maybe a good way to think about this is, think about some sequence that converges maybe to 0. If it's not monotonic already, then fine, that's an answer to this question. If it is monotonic and it converges to 0, then you can adjust it from being monotonic by just changing the sign on every second entry, for instance. So on every second term. So an example here, if we take the good old sequence 1, 1/2, 1/3, 1/4 that converges to 0, and if we change the sign, so that sequence is decreasing, so it wouldn't be an answer to this part 3. But if you want to change it to something that isn't monotonic, we could, let's say, change the sign on the terms with even denominator. So we have 1 minus 1/2, 1/3, minus 1/4, 1/5, minus 1/6, and so on. Okay, that is not monotonic anymore because it decreases at the first step and then increases and then decreases and then increases and then decreases and then increases. So it's very far from being monotonic. It's, it alternates between increasing and decreasing at every step. It still is converging to 0 because its terms are still fractions whose denominators are increasing to infinity. So the terms there are converging to 0. So that's a fine example of a sequence of real numbers that is convergent and is not monotonic. And it's a question just says give an example. All you have to do is give the example, and as long as you write enough to show me what your example is, that's perfectly fine. Just keep a lookout. Sometimes it might say give an example and give a line of explanation. So if it says that, you need to give some justification. But if it just says give an example, then as long as you write something that fully shows me what your example is, I am happy. Okay, where are we? Yeah, so part B is a specific sequence of real numbers defined by this kind of recursive relation. So we have a definition for the first term, a0, it's 4. And then after that, we have a description of how each term relates to the previous one. And we're asked to show some things about this sequence. So first step, write down the first 4 terms. That part is there kind of because I suppose we can do it relatively straightforwardly by just using this definition. And it's also because it kind of gives us, it's kind of a good thing to do anyway, because it gives us maybe a bit of a feeling of what the terms of the sequence are doing, so that we can get a sense of it, kind of, if you don't see that immediately. And then we have a couple of more questions. Show that the sequence is bounded below by -2, show that it's monotonically decreasing, and then explain why it can be deduced that the sequence is convergent, and write down its limit. So maybe the first one, I'll scribble an answer to here, and then I'll make some space for the rest of them. So we didn't do an example quite like this in the letters. So let's see. So a0 is 4. That's the first term. So this is an answer to part 1. A1. So the formula here tells us that the nth term in general, for n equals 1 onwards, is 1/2 of the previous term -2. So a1 then would be 1/2 of a0 -2, which is 1/2 of 4 -2, which is 1/2 of 2, which is 1. A2, the next one, would be 1/2 of the previous one, which is 1 -2. That's 1/2 of -1, so it's -1/2. And A3 would be 1/2 of -1/2 -2, which is 1/2 of -5/2, which is -5/4. Okay, so when you're answering questions, try not to squeeze everything into the margins like I've just done. Obviously make it as legible as you can. Okay. That is part A, or part 1 of part B. So we'll just make some space. So again, just our sequence here is defined by a0 is equal to 4, and an is 1/2 of an -1 -2. And that applies for n for the A1 term, the A2 term, and so on. So basically, once we know a given term, we can calculate the next one from that recursion. Okay, and so the next thing that we're supposed to do is show that the sequence is bounded below by minus 2. So okay, so here we have to kind of make use of this fact. And so I suppose if we can show that if a given term is greater than or equal to minus 2, then the next term is greater or equal to minus 2 as well, that somehow then we can kind of apply that all the way along the sequence, which is basically an induction sort of argument. So suppose that ak minus 1 is greater than or equal to minus 2 for some k. Okay, then if ak minus 1 is greater than or equal to minus 2, then ak minus 1 minus 2, which appears in the definition of ak, the next term, that's greater than or equal to minus 4. And that tells us that ak, which is 1/2 of ak minus 1 minus 2, is greater or equal to 1/2 of minus 4, which is minus 2, so that ak is greater than or equal to minus 2. So basically, this is saying that if a particular term is greater than or equal to minus 2, then so is the next term. Okay, so we know that a0 is greater than minus 2 because a0 is 4. So then this argument, which basically is what it's telling us, is that if a given term is greater than or equal to minus 2, then the next term also is. So this argument tells us that as soon as we know that a0 is greater or equal to minus 2, then a1 is as well. a2 is greater than or equal to minus 2, and so on. So all terms. So because one term being greater than or equal to minus 2 is enough to confirm that the next term will have that property as well, we can say that all terms are greater than or equal to minus 2. So this is a proof by induction, essentially, without the kind of language of induction around it. And you could of course organize it in the formal framework of a proof by induction if you wanted to. That's what it's doing. Okay, so basically we have this way of getting from one step to the next in the sequence that we can use to show that if a given term is greater than or equal to minus 2, then the next one is as well. And then as long as we know that the first one is greater than or equal to minus 2, applying that argument at every step tells us that they all are bounded below by minus 2. Okay, third part, show that the sequence is monotonically decreasing. So there we need to show that ak is at most equal to ak minus 1, that there are no increases as we go from one term to the next. So we need to show that ak is less than or equal to ak minus 1. And what we know about every term is that it's greater than or equal to minus 2. Okay, so ak minus 1 we know is greater than or equal to minus 2. And that tells us that minus 2 obviously is less than or equal to ak minus 1. So ak minus 1 minus 2 is less than or equal to, the minus 2 is less than or equal to ak minus 1. So ak minus 1 plus minus 2 is less than or equal to ak minus 1 plus ak minus 1, which is 2 times ak minus 1. And now we can say for any given k that ak is 1/2 ak minus 1 minus 2. That's less than or equal to 1/2 2 ak minus 1, which is ak minus 1. So we can say that the kth term, because of the whole sequence being bounded below by minus 2, we can show that ak is less than or equal to ak minus 1, which is exactly what it means to say that the sequence is monotonically decreasing, that each term is at most equal to the previous one. Okay, and finally, what we've shown at this stage is that our sequence is bounded below, and it is monotonically decreasing. So part 4, our sequence is bounded below by minus 2 in particular, and decreasing. And then we have a theoretical instrument, the monotone convergence theorem, that tells us that the sequence is convergent. So it's convergent by the monotone convergence theorem. And one remark about this, in case there is something like this, this step of showing that the sequence is decreasing, deducing that from the recurrence definition, I suppose it's possible to get sort of a little bit bogged down there. But in the first part, we're asked to state why it can be deduced that the sequence is convergent. So even if you aren't sure that you've managed to show that the sequence is actually decreasing, you can still say the reason why it must be convergent if it's decreasing and bounded below is by the monotone convergence theorem. So kind of, be on the lookout for things like that. And, even if you hadn't completely successfully completed part 3, I would still give you the credit for part 4 if you say the reason is because of the monotone convergence theorem. That applies to a situation where you have a sequence that's bounded below and decreasing. And then finally, the limit L must satisfy. So once you get to the limit, once you kind of plug into the recursion, the limit, it must, the terms are all sort of clustered at the limit. So if we put the limit itself, L, into the recursion formula that defines the sequence. So the recursion formula says that an is 1/2 of an minus 1 minus 2. So once you get to the limit, that step for getting from an minus 1 to an must actually keep you where you are. So it must satisfy that L is equal to 1/2 of L minus 2. an and an minus 1 both have limit L as you head out to infinity. So if you just take a limit of this statement as n goes to infinity, what you get is L equals 1/2 of L minus 2. And solving that equation for L tells you that L, no surprise, is equal to minus 2, which we had already identified as a lower bound for our sequence. Okay, so the limit is minus 2. Okay, so parts C and D. Part C is a theoretical element from the lecture notes. So there might be a few things like this. So, show that the harmonic series is divergent. In this year, you'll be able to kind of have a look there in the lecture notes and see how to go about that. And you still have to understand it, I guess, and convey it accurately. And then the last one is a few terms from the Maclaurin series of the exponential function of cosine x. So we are at 10 to 11. So what I'll do is add to these notes solutions to those last two parts and also to question 2. So I'll upload a kind of complete set of solutions here. And if anybody would like me to post some kind of extra video versions of that, I'm very happy to do so. Just let me know. So that kind of, I guess we're sort of at the conclusion of our lecture time as such. What I want to say to everybody who's joining us for the recording and who's here in the meeting is just thank you so much for your participation in this course. It has been a difficult year for absolutely everybody that's here and for indeed everyone in the world, I guess. And it's, it's really been a big pleasure to work with all of you and to interact with you. So thanks so much for your participation. I've really enjoyed our lectures and working with you. And I really sincerely appreciate that and hope that we will have a chance to meet in person and to interact in more direct ways before very much longer. So thanks for being here. I'm going to stop the recording here. You're all, please get in touch with me anytime if you have any questions, and I'm more than happy to correspond, and also keep an eye out for updates via emails to Blackboard and on the website. So the recording stops there. Thank you very much, everybody.